we start with the Z transforms. Every time we are required to find the Z transform, we'll always be given a discrete sequence. And this one in particular is an infinite sequence, and therefore its Z transform is defined as x of z, which is the summation from k equal to negative infinity to infinity of xk divided by z to the power k. So that means xk is the original sequence that was given divided by z to the power k. So all the time we're looking for the z transform, we'll always have z in the denominator. Wherever the sum exists and z is a complex number. Note that the process of taking the z transform produces a function of a complex variable z. So every time we take the z transform of a given sequence, we will have a function which has variable z. Therefore, we have a z transform pair, which is xk x of z. Note that when we want to do the reverse process, it would mean that we're taking the inverse of the z transform of x of z to produce the original sequence, which is xk. So therefore you use that notation, the inverse z transform of x of z producing the original sequence. And therefore, if now we have what we call a causal sequence, that means where the sequence starts from k equal to 0 to infinity, noting that for all values of k less than 0, we have xk equal to 0, then it is called the causal sequence, and therefore the z transform starts from k equal to 0 to infinity. Let's do some examples. We'll start with xk be given to be 2 to the power k. Note also that is for k greater than or equal to 0, so that means this is a causal sequence. So we go straight to the definition, which says that x of z is equal to the sum of xk divided by z to the power k for k equal to 0 to infinity. In place of xk, we substitute what we have been given to the power k, and then the denominator remains as z to the power k. Now we have to expand this series. So k note that starts from 0 onwards. So we substitute wherever there is k in that formula, we substitute the values of k. So we start with 0 and then 1, 2, 3, 4, depending of course on how far you've been asked to go to. And therefore we have now a series, which is 1 over z power 0, 2 over z and 2 squared over z squared, 2 cubed over z cubed, and to the power 4 over z to the power 4. Note that the first term is 1. And I'm hoping that we still remember the geometric series to infinity. As a recollection, let's note the following expression which holds. Sum to n terms is always given by the formula 1 minus r to the power n divided by 1 minus r, where r is the common ratio and a is the first term. Note that this sum to n terms, when n tends to infinity, its limit is a over 1 minus r. Therefore, we are able to use the sum to infinity formula, which is a divided by 1 minus r, so that we can be able to sum the series that we got in the last step, which has been rewritten here in the first step, noting that we have to calculate r, which is term 2 over term 1, which is also equal to term 3 over term 2. So we do the substitution. Let's see if we are going to get the same answer. The second term is 2 over z. First term is 1 over z naught. Term 3 is 2 squared over z squared. Term 2 is 2 over z. Both these expressions, they give us that r is equal to 2 over 7. And then we use that formula, sum to infinity, which is equal to a over 1 minus r. Substitute a, which is 1, because we know 1 over z to the power 0 is 1. Substitute 1 in place of a, and then we substitute 2 over z in place of r, and then we simplify. And that gives us the expression for x of z to be z over z minus 2. So therefore we know the z transform of 2 to the power k gives us z over z minus 2. Number 2, we've been given the sequence fk with a 0 for k equal to 0 and 1 for all other values greater than or equal to 2. Once again, we use the formula. We know now, based on the formula that has been given to us, we realize that k starts from 0 going forward. So that means this is a causal sequence again that has been given to us. So we're summing from k equal to 0 to infinity. Do the expansion and then substitute the relevant values. When k is equal to 0, we have the function or the sequence value to be 0. When k is equal to 1, again the sequence value is 0. That is why we have 0 over z to the power 0, z over z to the power 1. And then for all the other values, when k is greater than or equal to 2, we have the sequence value to be 1. Then we substitute 1 for all the other values. So it means that all the other terms will be 0 except starting from 1 over z squared going forward. So the first term for our series this time is 1 over z squared. So we have 1 over z squared. And then we calculate r. That means it will be 1 over z cubed divided by 1 over z squared. 1 over z power 4 divided by 1 over z cubed to get r to be 1 over z. Please check that and then simplify. And this is what we got, 1 over z squared times z over z minus 1, which simplifies to 1 over z into z minus 1. Then number 3, we have fk given to be 0 for all values of k less than 0, and e to the power negative ak for k greater than or equal to 0. So that means, again, we use the formula. Note that this is a causal sequence again. So we're summing k from 0 to infinity. And then we do the substitutions. Wherever there is k in that expression, we substitute the given value of k. So that means we're starting with 0, and then 1, then 2, 3, 4 onwards. And then we do the simplification. We know that e to the power 0 is 1. So that means the first term is 1. The second term is e to the power negative a divided by z. So we want a positive power of e. That's why we take it down to the denominator, noting that we'll have 1 over e to the power a times z as the second term, and so on. Then we do what we always do. Find the value for r, dividing the second term by the first, the third term by the second, and we got 1 over e to the power a z. Simplify, and that's the final answer that we got. Note that all these are causal sequences that we have been exploring. Now here are some exercises. Determine the z transform of xk, which is a to the power k. Fk now is 1 for all the values of k less than or equal to 0, and 0 for positive values. So that means your summation for number 2 starts from negative infinity to 0. And then you'll have ones on the left-hand side, but zeros on the right-hand side of 0. Okay, note the values here for 0, 1, up to 5. The sequence is 0, and you get 1 for values of k greater than 5. And also, we've got a causal sequence for number 4. Now, using tables, we have, according to rule 8, we have the Z transform of 8 power k equal to Z over Z minus 2. So it means that if the value of a is 2, then it means we'll have Z over Z minus 2, which we have already proven. That means if here we have 3 to power k, we'll have Z over Z minus 3. And then for b, e to power ak, note that it will always be Z over Z minus e to the power a. So that means it will be that exponent without k. So there is the second example. We have here e to the power negative k. So that means the coefficient of k here is negative 1. Hence we have Z over Z minus e to the power negative 1. And then we simplify, giving us ez over ez minus 1. Here are some more examples. Using tables, we are asked to determine the Z transform. Note that the Z transform is linear, so that means we can be able to take the Z transform of each of those terms. So the Z transform of 1 is on the tables, Z over Z minus 1, and the Z transform of e to the power negative ak, we had said is Z over Z minus e to the power negative a, and then we simplify. Remember that we do cross multiplication. Cross multiplication for the denominator, you multiply the denominators together. Simplify, remove the brackets in the numerator, and this is what we got. Please check whether you're going to get the same answer. Number 2, we've got now k a to the power k minus 1, and we realize that k a to the power k minus 1 is the derivative of a to the power k with respect to a. So therefore we can be able to take the derivative, the Z transform of the derivative. So hoping that we realize that the Z transform of k a to the power negative 1 is the Z transform of the derivative of a to the power k with respect to a. Interchange Z and d over dA. Z transform of a to the power k we already know is Z over Z minus a. And then we take the derivative of that. Note we use the quotient rule. Quotient rule, and note we are differentiating with respect to a. Quotient rule says denominator up first and multiply that by the derivative of the numerator. So that's what we did. Z minus a times the derivative of Z with respect to a, that's 0 because Z does not have a, minus the numerator as it is, which is Z, times the derivative of the denominator, which is negative 1. Remember, we're differentiating with respect to a, and then all of this is divided by Z minus a all squared. Removing the brackets, this is the final answer that we get. Number 3, now we're going to sine of AK. We use the summation, and note that here k is greater than or equal to 0. So we're dealing with a causal sequence. That is why the summation starts from 0 to infinity. And then we use the exponential form of the sine function, which is e to the power jak minus e to the power minus jak divided by 2j. And then Remember, we're multiplying that by 1 over z power k, and then we spread the summation sign. And we note that the first summation sign is the z transform of e to power jak. The second summation sign is the z transform of e to power negative jak. That is why we went straight to the tables using rule 6 or rule 2, and we got those. And then we do the simplification. Now note, when we get to the second last step, we realize that the numerator has those two terms divided by 2j. That is why they gave us sine A. And in the denominator inside that bracket, we have cos, but now it does not have divided by 2. Hence, we say 2 times cos A. Please confirm this and do the exercises that we have in the last slide.